Alright, we move on to our next topic. Now in this video we're going to define buoyancy. We're going to derive an equation to find what the buoyant force is, and we'll also we'll make connections with basically we're going to derive the equation for Archimedes' principle. I always have trouble saying that. So here's the deal. Okay, if you have a liquid, okay, you've all done this. Or if you haven't done this would be a great time to do it. Take an empty bottle of water and try to push that into a tub of water and see what happens. Okay, and you'll all realize that hey, the water, the bottle is going to be pushed out. Okay, now this force that the liquid exerts, this upward force that a liquid exerts on any object in it, is called the force of buoyancy. Okay, so it is the upward force on an object in a liquid. Okay, this is nothing but the buoyant force. Right. So if I have anything, whether it's completely submerged or whether it's partially submerged, the liquid is going to try to kick it out. Okay, this is the buoyant force. This is the same force that allows a balloon filled with helium to go up, the same force that allows a hot air balloon to go up, the same force that keeps you afloat in water, the force that keeps a ship afloat in water, and all those things. So we can do a lot of useful stuff with this calculation. So our goal here is to figure out this force. Now Archimedes' principle states the following. Okay, that the buoyant force on a liquid, buoyant force on an object in a liquid, okay, whether it's fully submerged or partially submerged, is equal to the weight of the displaced liquid. Okay, so the buoyant force on an object in a liquid is equal to the weight of the displaced liquid. So let's say that I have a container with some fluid, and I take an object and I submerge it. Okay, or not completely, but say partially submerge it, whatever. It doesn't matter how much I submerge it, but let us say that the submerged part of the volume is this V sub s. Okay, what this principle says is that the force of buoyancy, F sub B, is equal to the weight of the displaced liquid. Weight of the displaced liquid. Okay, now what is weight? Weight is nothing but mass of the displaced liquid times the acceleration due to gravity. Okay, but mass is nothing but the density of the liquid times the volume times everything. So what this says is that the buoyant force is equal to rho times V times G, and we're going to derive this expression shortly. And here I want you to know what rho is. Rho is nothing but the density of the liquid. Density of the liquid. Okay, not of the solid, the density of the liquid. V is the submerged volume. Okay, so the volume of the submerged part of the object, and G is our good old friend 9.8 meters per second squared, the acceleration due to gravity. So let us derive this expression. It's a beautiful expression, I like it a lot. Let's derive it. Alright, let's do it. Let's go. Okay, so let us, for our purposes, okay, instead of just taking partially submerged, let's just submerge the whole thing. Alright, let us say that an object of not this volume, we're just we're taking specific volume. It could be anything. It could be a blob. It could be anything. Okay, so let us say we have some object of say area A and say height h, and we're going to figure out the total force that the liquid exerts on this object. Okay, so what we know is that the force is going to be due to the force from all the elements of the liquid. Okay, all these things. Okay, we have force on the top, force on the right, force on the left, force to the left, and in all possible directions. And we're going to figure out the total force. Okay, so let's call the top force F top. Let's call the right force to the right be F right, F left, and we have F bottom. Okay, let us also say that the top of the fluid is some depth D, okay, from the top of the liquid. Great. So the net force, okay, the total buoyant force, okay, we're saying is equal to F top. All right, I'm going to write it in a vector form. F top plus F bottom, okay, plus F right plus F left. Okay, now what we know is that the object is not moving to the left or the right. All right, as a result of which the total force on the right hand side and the left hand side have to be equal and opposite. So what we know is that F right is basically the negative of F left. Okay, so these two terms combined give us 0 because they have to cancel each other out. Now the top and the bottom, however, are going to be unequal, and the bottom, you see, has to balance nothing but the top plus the weight of the object. All right, so let's figure out how to calculate the top and the bottom. We're going to go back to our equation for the pressure itself. Okay, we're going to write down the force on the top is pushing it down. So I'm going to write this as, instead of the vectors, I'm just going to write FB now for the force. This is the whole force buoyancy. I don't want you to confuse between the force bottom. Okay, so the buoyant force is equal to the force on the top, which is nothing but the pressure at the top multiplied by the area, but it's pushing it down, so I'm going to push it and put a negative sign there, plus the force at the bottom is nothing but the pressure at the bottom multiplied by the area that is pushing it up. Great. Okay, now we know the pressure with respect to depth. So the pressure at the top is nothing but P0 plus rho g d, where rho is the density of the liquid, okay, times A, plus the pressure at the bottom is equal to P0 plus rho times G. Now the depth of the bottom, okay, if you look at this picture, is D plus H. Okay, so D plus H, and I'm going to have to multiply all this by A. Great. All we need to do is some basic algebra and life is good. So we get negative P0A, negative negative rho G D A plus P0 times A plus rho G D A plus rho G D H A. Got rho G H A. Now let us look at all these expressions. Okay, a lot of things will cancel out. This guy cancels this guy. Okay, this guy cancels this guy, and in the end all we are left with is rho G H A. Okay, so this is my F buoyant force. I'm just gonna, okay, later I'm just gonna call it FB. Now what is HA? Okay, you guessed it right, nothing but the volume of the liquid. Okay, volume of the volume of the solid, the volume of whatever part is submerged. Okay, so this V is nothing but the submerged volume, and you see now we have F buoyancy is equal to rho GV. Okay, rho times V is nothing but the mass of the displaced liquid, so it is equal to mass of the displaced liquid, okay, times G, and this is nothing but the weight of the displaced liquid. So this is basically nothing but a proof of Archimedes' principle, okay, which tells me that FB is equal to this. Okay, however, the equation that you will use is going to be rho Vg. Just get used to this. FB is equal to rho Vg. Say it about 5 times. Okay, where rho is the density of the liquid, let's say V is the displaced volume, or the volume of the displaced liquid, and G is our old friend 9.8. So buoyant force rho Vg. Buoyant force is rho Vg. The force of buoyancy is, yeah, good job. All right, so that's what we get.